Now, my memory is not very good, but I think we covered the syllabus and we covered the research paper, right?
Yes.
Okay, so what we had left to do was my locator card, which is sort of good because it's changed since last time, and it may actually still change again. And this may actually change your I talked about on the syllabus, but I put the so far updated syllabus on Blackboard. So it'll be a little bit, office hours is the only thing that is different here. Any questions on anything we talked about before? Okay. All right, this is my locator card. This is for this first mini-term. My 8 o'clock class on Monday, Wednesday was canceled, so I'm in the office at 7:45 until about 9:30 when I have to go to my Calculus 1 class. Okay? That's on Monday and Wednesday, so those are office hours there. Calculus 1 is a 4-hour course, so it goes a little longer than normal. It goes to 11:10, so I'll try to get back in the office about 11:15 or so. And then I'm in the office until, this was the change, put me in a Math 098 class. Now, I have to put down when I'm at lunch, but I usually bring my lunch, and I usually eat in the office. Even if I don't bring my lunch, I buy it in the cafeteria and eat in the office. So I'm there most of the time for lunch, so you're welcome to come by then too. It's just, I hope I won't spit food at you. Okay, so, but then definitely office hours before and after, and during if you need to come. Now, this may still change. I found out at the end of the class yesterday, the Wednesday class, that one of the students has another class starting at 3 o'clock. So I'm going to talk with the class on, most of the others had left, so I'm going to talk with them next Wednesday because, by the way, there is a good news, bad news situation coming up. The bad news is there's no class next Monday. It's Martin Luther King Day. It's a holiday, so no classes. Sorry about that. The good news is it doesn't affect us any, because we do have class. Well, we meet on Tuesday. So, you feel better about it now. Okay, so next Wednesday, when I finally meet again, I'm going to check with the class to see if we can move up to 1:45 or even 1:30, so that that guy won't be missing as much class when he goes to his 3 o'clock class. And the other thing, Dr. Bryant usually uses my computer in physics class, and it's supposed to start at 3 o'clock, but he said he could start at 3:15. So that's still awfully tight. So this may change, and if so, I'll update this again. Okay. But then after that class is over with, whether it's 3:15 or whatever time it turns out being, then I'm back in the office until 5:15. Most days. Now, a lot of times I'll be after 5:15. Sometimes I'll have to leave right at 5:15. This is a really dumb reason, but it's true. We have a young dog. She's a sweet young dog, but she gets a little tired of being cooped up in the house all the time while we're at work. So every now and then my wife said, she's so wired at night, I need to rest. Let's get her to doggy daycare. So, and that's usually on a Wednesday. And if I take her to doggy daycare, then I have to leave here by 5:15 because they close at 6. And they're in Homewood. So I have to get, all the way across, the county almost to get there before 6 o'clock. But other than that, and like tonight, I'm going to have to leave at 5:15 because we happen to have a meeting, I think at 6:30, so I have to get home, grab something to eat, and get to the meeting at 6:30. But most times, I'm here past 5:15. Okay. Tuesday, Thursday, when we meet, I do have an 8 o'clock class, so this class is at 9:30. And as far as I know, they're going to let it run, mostly because of those other 2 students. In fact, y'all can't go to the Birmingham campus, and it's the only other time you can take it. Now, physical science, that's the question mark still. There were only 7 paid students here on Tuesday, but they said don't cancel it and let those 4 unpaid students maybe add to it. So I'll see today. If we don't have 10 paid students, and all those students, the 7, all the ones that were here, they weren't all here yesterday on Tuesday, but if all that show up can take something else, then we'll go and cancel that class. And then I have a bunch of office hours here for the first mini-term. Second mini-term, that class is made already, It can't start at 12:30 because there's auto mechanics in that, and they are on a block schedule, and they are in class until 1 o'clock. So we start that class, the 112 class, at 1:15, and then the class will go till 3:45, and then the lab goes to 5:45, and then I'm off campus at 6. So that's second mini term. That class is made. I already had 18 paid students or something like that. So I know that one will work on second mini term. Then on Friday, I'm on the Birmingham campus most Fridays, and it's the academic building, which is the B building. We're in 122, which is Dr. Pruitt's suite of offices. I'm in the copy room behind Miss Saxon's desk. And I usually bring a little snack. I don't eat a full lunch usually that day, so I'll bring a little snack and just eat in the office there too, so you're welcome to come by. Now, I may not have said it before, but let me say it now. They love calling meetings on Friday, and they called one for tomorrow, okay? I saw the email, but I haven't opened it to see the details. So what I'm going to do is see, number one, which campus it's on. If they happen to move on this campus, which they don't usually, but sometimes they do, if they happen to meet here, then I will be on this campus tomorrow. But if we're on Birmingham, I'll be on Birmingham. And again, I haven't seen the email, so I don't know the time. Usually it's 9 or so, but sometimes they move it to the afternoon. So it may actually be after I'm supposed to be on campus, which would be a real joy. Okay. Or sometimes maybe starting at 11 and go to 1 or something. It's supposed to be off that campus. But anyway, I'll find that out. Sorry. All right. So that's my locator card. Any questions on that? Okay. The other thing that we need to talk about before we can actually get into the math now is safety. And I know there's only 3 of us, but we still need to think about this ahead of time so when something happens, we don't think, what do we do? No, that's not the time. The time to find out what to do is now, and then when something happens, you just do it. Okay, so 3 areas of safety. Can anyone think of what one of those might be?
Are you talking about the things that we prepare for?
Second?
Are you talking about like the things we prepare for, like a fire or whatever?
Yeah, exactly. So let's say we have an internal emergency, like a fire, or a chemical spill, or a boiler blows up, or something like that. That's in the building, and we need to get out. Now let's start with the maybe worst case scenario for us. It wouldn't be too bad for most of others. Let's say it started in this room. Let's say my computer spontaneously combusted, and had a fire started here. It starts here. What do we do? Second? Oh yeah, we leave and let the building burn down, and all those other people don't even know it's fire. Okay, that's very kind of you. Okay, I'm going to watch you. Okay, what should you do first? We will leave. You're right. Oh yes. Okay, now who do we call? Ghostbuster. No. Okay. Okay. Now there's 2 ways to do that. The very best way is to call campus police. Now, Lieutenant Tate, who's in charge on this campus, gave me this number, so I assume it's correct. This supposedly is the number that the duty policeman on this campus has in his or her presence all the time they're here. When they swap over, the next person gets it. So this should be in the hands of someone who's in charge. It's 426-3654. Okay? If you want to put that in speed dial on your handy-dandy little phones, that would be the best first number to call. 426-3654. 426-3654. This is his handwriting. He wrote it down, LSPD, Los Angeles Police Department. Okay? And he said that's the phone on the person on this campus is here. It's not going to the Birmingham campus, it's here. So, someone do that. Now, if you don't have that, it doesn't go through, some reason like that, the next best number is 911, exactly. And so we do that. So we've notified the officials, but what else do we need? Then we leave? Well, if we know it's burning, we need to do what? Pull a fire alarm, yes. Okay, so somebody's dialing 911 or the campus police or whoever. The other is maybe two going down to the nearest fire alarm. Where is the nearest fire alarm? Anyone? Here's the map of the building of the second floor. Okay, where's the nearest fire alarm? Anyone know? Nowhere on the second floor of this whole part of the building. This building was built before that was required. There is no fire alarm in the old part of the building. But there's a newer part of the building, see the surfaces wing down here in the middle? There is. So how you get to the nearest fire alarm, go out the door here, hang a left, go down that half flight of stairs, don't go out, go to that corridor that goes between the restroom and 254 that comes out right there at the financial services office, and on either wall, the one just in here or over here, both places have fire alarms, whichever the easiest and quickest to get to. Okay? So, one or two of you go down and pull the alarm. Somebody else is called 911 or campus police. Campus police first and 911 second. You can't get them. Then what do we do? Is that when we leave? And just let my papers go up and smoke in the desk and everything?
I don't know.
What do you think we should do?
Well, how about putting it out? I'll be in charge of that, but you may need to help me. What do we use to put out a fire? Yeah, it's a fire extinguisher. Where's the closest fire extinguisher? That was what I'm getting at.
Is it
Huh?
with the fire alarm? With the fire alarm?
Okay? Actually, you see where I'm standing here?
Yes.
Within 5 feet. Look right on the wall, right there. I mean, you can't get much closer than that. Fire extinguishers they can put in all parts of the building. Fire alarms they have to rewire and everything. So it's just outside the door here. And I bet that at least one of you has always said, wouldn't this be cool to break that glass, you know? Yes, okay. I thought I had picked that. Okay. You get to do that then. Okay. And if it was, yes.
Why is it always breaking the glass? It's like so that it won't get hot when you have to open it or something?
Here's my guess on that. I don't know the exact answer. But I think if it was open and accessible, people would rip them off. So they put them in glass, so they're somewhat secure, but if you're going to rip it off, you have to break the glass, and that's probably going to be hurt or something like that. So that's my guess. They couldn't put it in a locked box because who has the key? You know. So and if they put it in just a box that anyone could open and get, so they put it in glass. So you have to physically break it to get it out, just like the fire alarm. You have to break the glass to make it ring. Otherwise, people would be switching it all the time, probably. Oh, I have passed that yet. So, I don't want to plant that in your head. I got to watch you. Okay, I know that. All right. Okay, now, let's say it didn't start in this room, and we hear the alarm go off. What do we do? Or after we've done all those other things, what do we do then? Leave. Okay, now how do we leave? Okay, the closest exit. We don't want everybody leaving out the same door. That makes a bottleneck, and that could be people get trampled. So where's our closest exit? We go out of the door here, hang a left, go down the half flight of stairs, hang another left, go down the full flight of stairs, just like we did for, we haven't said that yet. Okay, and then we go out of the building. Okay, and in the old days, they told us to go at least 75 feet away from the building, straight away from the building, in that grassy area where we used to go, and just hang around there until we know it's all clear, or we get up report otherwise. Now they're saying, don't just go there. Here's the diagram. Here's our classroom right here. Here's that exit right there, and we go down into that parking lot down there. Okay, go into the parking lot. It's a little bit further, but it should be very safe, and it's all messy in the grass and muddy and stuff like that. So down in the parking lot. Okay. And now, do you say, ha, okay, building's on fire, no more classes, I'm out of here? No. Okay? Because, now all three of you look pretty healthy now, but Daniel may have leg problems, I don't know. And what if one of you has damaged a foot or a leg or something like that and can't move as easily? I'm going to be with you, last one out, making sure you're out, everybody's out. And if I need to, I might ask one of you to help me with Daniel because he's pretty heavy. Okay, whatever. But anyway, we're out. And when I get there, I'm also carrying my handy dandy little roll book. Because when we get there, I have to call roll to make sure we've accounted for everybody. Now, in this bigger class, I think I can handle it, okay? But in like my previous class, 28, 30 students, something like that, it's I can't tell looking at everybody's here. So I do call the roll, and they come around and check, is everyone accounted for? If we can't account for someone, the assumption is they're in the burning building. So someone has to go back, risking their life and health, seeing if they can find you when you have gone off to talk with a friend or driven home or something. So don't do that. Stay together at least until we get word of something else. They may say, no, it's just one room. We can rearrange classes and stuff like this. It's all safe, or whatever. But hang around until they tell us the directions of what to do next. Okay, so there's internal emergency. Fire, chemical spill, explosion, something like that. What's another type of safety issue? Weather, yes. This is spring term, right? Okay? This is the term for tornadoes. So they can happen any time during the year, but this is the time when they happen most frequently. So what we listen for now, this class, Tuesday, Thursday, we probably won't hear the test alarm. Those are usually Wednesdays and Saturdays, so that won't be up. So if we hear an alarm, we need to do something. What do we do for the weather emergency? What's the rule? Okay, you go down and interior. That's it, exactly. So where do we go? We go out the little door here, hang a left, go out, go down the half flight of stairs there, hang another left, go down the full flight. Rather than going out, you don't want to be out when it's weather emergency, you go in. Now, interior down here, and the first floor looks a lot like this, but it's not exactly the same. The first thing you see there are two restrooms, male and female. Okay? They're not really bad places to be because you have their interior rooms, the walls are close together, and you have a lot of corners. The greatest strength is in a corner, the next greatest strength is in a wall, open in the middle of the room, not the greatest strength. Guess what? The restroom doesn't have very much in the middle of the wall. And everything back here is soil. That is built against soil. So there's nothing really to come down on you, So that is the back walls are a great place to be. Now, the restroom may not be your first choice of where you'd like to spend a couple of hours, okay? Especially if it really is a tornado or something, there's a real good chance we're going to lose power. And the restrooms don't have emergency lighting, so you're in the dark in the restroom, maybe not the best place to be. But, it's a safe place. Right next to the restroom, actually there's a few little steps down, 2 or 3 steps down, and then there's an office there. It's the academic dean's office. Now, most of the time it's empty, and it's locked up and you can't go in. Okay, but if anyone is in there, he's the academic dean, the associate dean, and sometimes Dr. Briggs or someone else comes over and uses that space. If someone's in there and they invite you in, yeah, it's a pretty good place to be because it's interior, lowest floor, interior, and has pretty close walls and lots of corners. Okay? Going on down the hall there's room 160. Were any of you involved in math? You may have been in a classroom down there, 160. Underneath our 254, the classroom underneath that. That's a big open room. But the back wall is really solid, okay? So that's not bad. The corners aren't bad. The other walls are safer than the middle of the room. I wouldn't get in the middle of the room. Okay, then you go through those glass doors into the library space, and the first thing to your right there is that little computer lab. And there, the walls are fairly close, especially that back wall is a really solid wall. So that's not a bad space. It'd be better actually than the classroom. The next room to that in the library is what I call the reference room. That's where the globes are, the atlases, and that kind of stuff. It's a bigger room than the computer room, probably not as big as the classroom. So the middle of the room would be the best, but that back wall, again, is really, really safe. Okay? The corners aren't too bad. It does enough shelving, so if you do have blocking of the building, especially some of the shelving may fall, so that might not be best. Okay, you don't want anything else in the library because everything else in the library is windows. You don't want to be in an exterior room because of tornadic conditions, all sorts of projectiles, tree limbs, pieces of debris can come flying through a window, broken glass, projectiles hitting you, damaging you. You don't want to be there. So stay out of these others. But actually, one of the safest places to be is the hallway. And, or I say best places to be. The walls are close, that's better than a classroom. You don't have any corners, that's not as good as a classroom. But the big advantage is the hallway on both ends have emergency lighting. So if the power does go off, all these things back here, you're pitch black. Okay? So you're better off. The hallway is maybe the most pleasant place to be. You can sit along the wall and talk to friends, that kind of stuff. So we go down. Again, I'm the last one out of the room. I go down with the slow student. I get down there. I call roll again. Again, this is actually pretty easy. And once we call roll, then if you want to go mingle with friends. Do not think, oh, I got to get home and get the dog. You know, no, you don't. The car is the worst place to be. One of the worst places to be in a tornado, because they get things thrown around like crazy. Okay, so don't think about leaving. Okay, because if you do, and we can't account for you, someone has to assume you're still upstairs somewhere and go upstairs and risk life and health being in a place where things could come through walls. Okay, any questions about weather then? One other safety issue I never even used to think about it, but nowadays we have to. Say again?
Intruders?
Yes, active shooters. That's what they call them. I'm, hard of hearing. So if y'all start hearing some pops that sound like they could be gunfire, stop me, okay, and say, listen, that could be. So what do we do? Okay, so we think we hear an active shooter somewhere. What's that? I can't quite do what you're saying. Yes, that's a very good thing to do, but we want to do something. Lock the door. Now, here's an issue here, folks. I have a key to this door. Now, not all your instructors may have keys to the classroom. Some of them will, especially as adjuncts, they may not. There are no buttons or anything to lock this from the inside. I have to physically, and there's no key on the inside, I have to physically go on the outside and lock the door from the outside and then come back in and you can close the door. Okay, so I can unlock it, but I don't want to. Okay, and I come back in and close the door. So it's locked from the outside, but it's still unlocked from the inside. So and I'm going to say him. Most active shooters are hymns. There's been one that I've read about that was one. Most of the others are the hymns. So it's going to be the guy, the dude, you know. Okay, but we have another entrance here. So what do we do here? Okay, well this door does have a button on the inside. So I press that button. It locks here, but it doesn't lock there. So we just locked ourselves in the room, but he can still come in. So we don't want to lock this door. Now this door has a deadbolt. I don't have a key for it. That would be a great one. I don't have a key for it. So that next door is just like this one. It's locked from the outside, but doesn't from the inside. So we go over and press that button. Now there is a class in there. I don't know who the instructor is, but my guess is he or she may not have the key to that door, and I don't either. So we might invite them to come in here. We close that door, lock that door, close it. So the reason we close the door, notice these doors have a little glass. They can see it. Okay, close this one, they can't see that anyone's in here. And that door is locked. Okay, so, and we close this one too. And then we do what you said. We all, even those folks over there, get back here. Because gunfire can come through wood, certainly can come through glass, hard to get through concrete block. So we all get over here, everybody turn off the lights, very quiet, just settle down, ease down, until we hear someone we know officially is saying, all clear. Okay.
And what if they're seen through that class?
What's that?
What if they're seen through that class? What if we make a mistake and we get in this room, see through that class?
Okay. If they get through here, into here, okay, then if they're in there, we go out here, you know. But actually, people ask not that same question, but if it came to that, and they say you're not supposed to say this or do this, but I'll tell you what I think should happen. If they get in here, I go for the shooter. I'm 67. I've lived most of my life. You're the future. You get out of here, okay? And I will block him, talk with him. I'll do whatever it takes to get y'all out of here, okay? Now, some of your young instructors may not want to do that, you know, but the kids at home or something like that, I don't blame them. I wouldn't either. But I have basically, I mean, I'm on the waning years, okay? But if he did get into there, y'all get out, and I'll try to distract him, talk him out of it, or whatever, you know. But you go to safety. Okay. My last class says, "Hey, we can attack them too." And I said, "Well, let me take the bullets. You can take the." All right. Okay. It's easy to say. I don't know if I'll have the guts to do it, but hopefully I will. Hopefully it'll never happen. It's only happened with one community college that I've heard about. Universities, it's happened a few times there, and then other places. And really, it's a very, very rare thing, but it's something we need to think about beforehand. So we don't think, oh, I wish we'd have locked that door. You know, we know what doors will lock and not lock, so think on it. Okay. Any questions on safety? All right. Let's hit some trig. Enough of this stuff. All right, from current slide. All right. Anyone know what trigonometry means? All right. How about metric? Meter, measure. That's what the last part means. To measure and almost think triangles. The measurement of triangles is originally what it means. But we're going to go several sections and hardly mention a triangle. So it's really broader than that now, too. But that's really where the word came from. But before we even get there, 4.1 is going to talk about radian and degree measure, two different ways that we measure angles. So first we're going to describe angles. Then we're going to use radian measure to quantify angles. Then we'll use degree measures to quantify angles, and then we'll use angles to model and solve some real life problems where the rubber meets the road, what we're all after anyway. Okay? So let's first talk about angles. Okay. As derived from the Greek language, the word trigonometry means measurement of triangles. But like I said, for a while now, we're not even going to mention a triangle. Initially, trigonometry dealt with the relationships among the sides and the angles of triangles. And we will do lots of that before the term is over. But to begin with, we're not going to deal with that. But we will get there. But let's first talk about what an angle is. And by the way, the word triangles. What does that mean? Three angles. Tri meaning three, angle meaning angles. Okay? So triangles, three-angle structure, which means a three-sided structure. So an angle is determined by rotating a ray, which is a half line. It has one endpoint that is fixed. The other one goes forever. A line goes forever in both directions. A half line is in one direction only. Rotating a ray about its endpoint, however much you do. This would be a small angle, a bigger angle, greater angle, larger. Okay. So that's what an angle is. It's the measure of how much you rotate a ray about its endpoint from some initial position. Okay? The starting position of the ray, when it started, that's called the initial side of that angle. So if it started down here, why, I don't know. If it started down here and you rotate it up to here, then this forms an angle. The end, that fixed endpoint, that's the vertex. Okay? Has no limit here, has no limit there. This is a measure of how far you rotated this from its initial position to its final position. Initial side to terminal side. Okay? The angle is that measure. Okay? You don't measure that in lengths. You don't measure it in masses. You don't measure it in anything except a mental concept. Okay? And it's an angle measure. The endpoint of the ray is called the vertex. I already said that. Now, this perception of an angle fits a coordinate system in which the origin is always the vertex. That's a real neat way to have it. In reality, it's not always like that, but if you can picture it and mentally get it there, and if you can rotate that initial side without changing the angle any until it's on the positive horizontal axis, that's a great position for it. So we call this the standard position for an angle. Initial side on the positive x-axis or positive horizontal axis, terminal side wherever it happens to be. So this angle is moving this way, and this looks like the same one we had before that was like this. You just rotate it like that. So there's your angle in standard position. That's such an angle is called standard position. Initial side on the positive x-axis, the vertex and the origin. Make sense? Now, with that in mind, I don't know why this is. Either geometry people or trigonometry people are backwards, or the original clockmakers were backwards. Because a positive angle is a counterclockwise, and a negative angle is in the clockwise direction. To me, that almost seems like it shouldn't be that way. But that is the way we do it. Now, part of that, and I don't know if there's any real reason for this or not, if this is the reason, but at least it kind of makes sense. What's true about, okay, these two axes breaks the plane into four pieces, and we call those quadrants, right? We call this the first quadrant. What's true about the first quadrant? Everything's positive. The horizontal axis is positive, the vertical axis is positive, because we take positive to be to the right and positive to be up. So everything's positive in the first quadrant. Okay? Now, I don't know if the angles determined this, or if the geometers determined this, or who determined it, but they named this the second quadrant, and therefore you're going counterclockwise. Well, over here, the x is negative, but the y is still positive. Down here, it's negative, negative, and over here, positive x, negative y. So why could they name this 2, 3, 4? I don't know, but this is how they number it. So this is why counterclockwise is positive. Counterclockwise is positive, whether that's the reason or not. That's how I remember it by. Now, so therefore, if you're going clockwise, you're talking about a negative angle. So angles are sometimes labeled with the Greek letters. Alpha, beta, the most common, the most popular is theta. I don't know why, but it is. It's not the third letter. Gamma is the third letter of the Greek alphabet, but they love theta. Okay? Now, that's not always the case, but that's very common. There will be times in later chapters we'll name the angles capital letters A, B, and C. Okay? And once you get into vectors and things like this, you usually refer to anything to be an angle. But the most common is the Greek letters, and they're usually lowercase. This is a lowercase alpha, lowercase beta, lowercase theta. Theta is the most popular, like X is everybody's favorite variable. You know, Y and Z are fine variables, but everybody loves X, everybody loves theta. Everybody loves Raymond. Okay. And the A, B, and C, the capitals, are often used in triangles. We're not in triangles yet. So, in this figure, note that the angles alpha and beta have the same initial side and the same terminal side. Here's alpha, and there, look. Oh, I'm sorry. They told me this one's strange. That's not, okay. Sorry about that. Okay. this alpha is positive, that beta is negative. This alpha is positive, but this beta is also positive. So beta doesn't have to be negative. This is a positive beta, but you've gone around all the way around and got back to the terminal side. Okay? Now, so these two illustrations, alpha and beta, have the same initial size and terminal size. Same initial side and terminal side. These are going in opposite directions. These are going in the same direction. The one just wrapped around. So when they have the same initial side and terminal side, you call them coterminal. Because you always assume the initial side's the same if it's in standard position. If they have the same terminal sides, they call them coterminal. Now, I'm going to jump ahead just a little bit. Okay. If you look at this one, okay, I'll force myself not to jump ahead. We'll get there. Because I was going to ask you something that's going to jump ahead of the book too. So let's first look at radian measure. What in the world do we mean? Has anyone ever seen a radian before? No, it's a mental construct. You can determine the measure of an angle by the amount of rotation. That's what an angle is. The amount of rotation from the initial side to the terminal side. Something we've said about 3 or 4 times. Okay, all right. One way to measure the angle is in radians. Now, here's the unusual thing. When I say that, if I say you measure the desk in inches or feet or yards or meters or centimeters, that's giving a unit. And you say, I'm measuring the angle in radians, radian really isn't a unit, okay? We'll treat it like it's a unit, but it really isn't, okay? And we'll get there in just a minute, okay? This type of measure is especially useful in calculus. Now, you're going on to calculus, right? You two probably won't be, yeah. But anytime you're dealing with calculus, just about any time, you never deal with degrees. It's always in radian, and there's a reason for that. So what do we mean by radian? So here's how you define it. Now, you have a circle here. And like I said, we say trigonometry is a measure of triangles. And yet we're going to start with circles. Okay. Not a triangle. Almost looks like a triangle here, but it's still not quite a triangle. Now we're going to put the center of that circle at the vertex of that angle, okay, at the origin. So everywhere on the circle, the distance from the origin to the circle is always the radius of the circle. That's the definition of a circle. Okay. So the radius is always there. Okay. Now, if you were to spin this initial side a certain distance up here, and you're measuring the distance as you go. By the way, this is called an arc. It's a portion of a circle, a curve, and that's an arc. Later, Daniel will get into calculus and he'll deal with arc lengths and things like this. Well, that's S. But S would be very small there, larger there, huge there, bigger there, yeah. But when S is exactly the same as R, in other words, your arc length is exactly the same as the length of your radius, then the angle that makes that true is called 1 radian. Okay? Now, I don't like the way they are approaching it, but this is how they do it. To define a radian, you can use the central angle, that's the one from the origin, of a circle, okay, with the radius r, whose vertex is at the center of the circle. The radius, vertex of the angle is the center of the circle, shown here. When the arc length is equal to the radius, then you have 1 radian of motion. Now, if it was a bigger circle, there's a circle out here, the radius would be longer, but the arc length would be longer, and it always would be that same angle would always cut exactly one radius of arc length. Always. So basically what a radian is, and they're going to say it later, I'm going to say it now, it's the ratio of the arc length to the radius. That's what it is. The ratio of the arc length to the radius. And that, frankly, is where I think the name comes from. Ray means ratio. So this is one radian. Okay? When the arc length is less, you're less than a radian. Greater, it's more than a radian. So it's the ratio of the arc length to the radius. When it's exactly equal to it, you have one radian. Okay, so here's the definition of a radian. Here they show it. One radian is the measure of a central angle theta that intercepts, that's a strange word for it, an arc S equal in length to the radius of that circle. Okay, figure we just had. Algebraically, that means your theta, your radian measure, is the ratio of the arc length to the radius. Now, think about this. An arc length is some distance. Think of a paper tape that you're walking along a circle and you did the tape along the circle, and wherever you stop, that would be the arc length, right? It curves right through the circle. That's your arc length measured in what? Inches, feet, yards, miles, furlongs, whatever you do, centimeters, whatever. Measure the radius in the same thing. You use the same tape, okay? So the ratio of these two is a dimensionless quantity. That would be 3 inches over 3 inches, or 6 inches over 2 inches, or whatever it is, they're measuring the same thing. So basically, your angle measurement has no unit, and yet we'll say it's a radian. Well, it's a ratio of two things of the same unit. Where theta is measured in radians, notice theta is equal to 1, when S is equal to R. Obviously, right? Now, let's go back a slide. Can anyone remember, I'll first ask a simple question. What do we name the distance around the circle? Circumference, very good. Circ, obviously meaning circle, and ference means measure the circle. That's circumference, okay? Now, so one circumference. Does anyone know what the formula to get a circumference of a circle is? You got it exactly, 2 pi r. So the circumference of that circle, and I'll call that capital C, that just to have some name for it, is 2 pi times the radius r. Perfect. That's exactly what it is. Another definition would be pi d, but this one's better for our purposes. Now that circumference of the circle is the length of the arc of that circle. So this would be, for a circle, this would be your arc length. S is equal to 2 pi r, right? The arc length of that whole circle is its circumference. And what was the radian measure? The ratio of the arc length to the radius. So back here, we will divide both sides by r, and this gives you your theta, your radian measure, and guess what it is? 2 pi. Now what is pi? Besides that good thing we eat at Christmas? No. What is pi? It's what? Okay, it is a number. It's not, it's one of those strange numbers we call irrational. Okay? It has nothing to do with gender, by the way. Okay, never mind. Maybe we'll take that out. Okay, all right. It's a number that cannot be, oh, this is so bizarre. We say S over R, that's the ratio of two numbers we say, but here's the bizarre thing. An irrational number cannot be expressed as a ratio of two integers. Okay? A rational number can be expressed as a ratio of two integers. 3.7, 0.5, 1/2, 7/10, whatever. Those are ratios of two numbers, two integers. Even though this is a ratio of two numbers, they will never, ever, ever be integers. Okay? I mean, both of them. One could be, but the other won't be. It will always be some portion of that. And okay, that's a rather strange point. So pi is an irrational number. You said 3.1416, we sometimes say, but it's really 3.14159. And the thing that makes it an irrational number, if it was rational, at some point it would either terminate and not go any further, or it would start repeating a set of digits. Like if it was 3.14151415141514, that would be a rational number. But 3.14159, blah, 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 and they've carried it to millions or billions of digits, and you never start repeating any patterns at all. It can't. Now, it's not the only irrational number. Square root of 2 is an irrational number. Square root of 3 is an irrational number. Square root of 5, square root of 6, square root of 7, square root of 8, square root of 10, square root of 11. There's tons of other irrational numbers out there. Pi is just another one. Okay? There is another one that you think we'll run into in this course, but you may have run into in 112, E. Remember that one? 2.7, blah, 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 blah. That was an irrational number. Well, pi is an irrational number, and 2 pi is exactly one trip around the circle. Any circle, the radian measurement of all the way around the circle is 2 pi, right? So then what would you guess the radian measurement halfway around the circle would be? Pi, exactly. And how about a quarter way around the circle? Pi halves. And half of that? Pi fourths. A third of this would be pi 6, pi thirds, 2/3. So you can split up the circle into fractions of pi. Okay? That's jumping the gun a little bit more. Okay. So here is for a full circle, because the circumference of any circle is 2 pi r units, just like you said, that's the formula for it. It follows the central angle would have to be counterclockwise, would have to be, if s is equal to 2 pi r, then the ratio of arc length to radius is always 2 pi. So one trip around the circle is always going to be 2 pi. Now what I was wanting to say before, and I didn't feel like I should, let's say it now. What's the difference between alpha and beta here? Those are both measures of angles. We don't know what it is, alpha, but the beta, if you look at this, it started here, went all the way around, guess how far it went down? 2 pi radians plus alpha. So anytime you have two coterminal angles, they differ by 2 pi or some multiple of 2 pi. I might have gone down there 15 times, but it's some multiple of 2 pi. Okay. And how about this one? The difference between these two. Well, let's start with alpha and subtract a negative number, beta. Remember, beta is negative. And you subtract the negative number, and you now have 2 pi units, because that makes one circle. When you subtract the negative number, you're really adding. So add this to that, and you got exactly 2 pi. So anytime you have two coterminal angles, their difference is going to be some multiple of 2 pi. Always. Always. Okay? All right. So one full revolution counterclockwise is the arc length of 2 pi r. But counterclockwise, or clockwise, it would still be 2 pi r. It would be negative then, because it's a negative. Well, no. Yeah, because the angle would be negative. Okay. Moreover, because 2 pi is approximately 6.12, because you said pi was about 3.14, right? So that's 2 pi. There are just over 6 radius lengths in a full circle, okay? In other words, if this is 2 pi radians, okay, and that's 1 radius, 2 radius, 3 radii, 4 radii, 5 radii, 6 radii, plus a little bit more, 0.2, about a quarter of a radius left over. There are 6 full radii here plus a little bit, okay? And because the units of measure for S and R are the same, this is what I said before, the ratio has no units, it's just some real number. But we usually give it the unit of radians, but it's not really a unit. It's just how many ratios of the arc length to the radius you have. But we call it radians. Okay. Because the measure of an angle, okay, we've already hit this. 1 full circle is 2 pi radians. Then halfway around is pi radians. A quarter way around is pi halves radians. And 1/6 of the way around, which would be about like this. Okay, go back here to this one. It's approximately 1/6 would be just about that. Not quite. That's a little less than 1/6. But that would be awfully close, so that's 1, 2, 3, 4, 5, 6. A little bit. So a little bit beyond that is exactly 1/6 of the 1 pi thirds radians. Okay? This is a little bit less than pi thirds. 1 radian is a little bit less than pi thirds. Well, this way. Yeah. Yes. Hey. I'm sorry? Oh, absolutely. Yeah.
Hey guys, how y'all doing? I think you were in another class. Were you in another class? So you're the only one that did wrong. Okay, and I'll leave you some just in case you have other classes. The MLK Day is Monday. And so we are partnering with UAB to do a joint service project.
Oh, fantastic.
Yes, and so we're just trying to get students to come out and participate. That's the information right there. Whew, I'm out of breath. So, yeah, that's the information. Monday we'll meet at UAB at 10 o'clock. If they need transportation, they can meet at the Birmingham at 9 o'clock. And we'll transport from Boston to UAB. There'll be a panel discussion. Mayor Woodford will be there. We're serving lunch, and then we'll disperse to our service sites. And we will, I don't think this was confirmed when I saw you guys. So it has been confirmed. The service sites have been confirmed. And Lawson will primarily, like, once again, if you drive, you can go wherever you want to go. But if you want to partner, if you want to actually do Lawson as a team, we will be cleaning up the District 7 area. Which is over there by District 7.
Oh.
Which is over by the Birmingham campus.
Oh.
That Winona area will be doing a
nice.
Yeah, so you can let your other classes know.
How about telling these people who you are? They may know already.
Oh, I'm sorry. I'm Miss Bar. I think I know because I know they were in another class and he comes to the work room.
Oh, I see. Okay, so they all know.
So they
you.
know me.
Okay.
Do you know me? Yes. Okay, yeah. All right, but thank you so much.
Thank you. Absolutely.
Other classes. No, I'm sorry. I'm running out of papers, but my number's on there. Or if you get a chance to make more copies, feel free. And my number's on there. If you want to call and ask for a copy, I'll go get some more.
Okay. Well, actually, I just have one more class to set. Well, yeah, I'll probably need all this.
All right.
Thank you.
Thank you.
Okay. Sounds good. UAB is real close to where I live, so I won't be coming to college. I might go there. But I got to check with the boss and see if he already has plans for me. Okay. All right. So let's think about this then. If 2 pi is 6.28, then let's divide that by 2 and you get 3.14. And then divide that by 3, pi thirds, that's just a little bit more than 1. So this is 1 radian. So pi thirds radian is just a little bit more than 1 radian. just a little bit, just a small amount more, just to give you an idea. 1/6 of the way around the circle. 2 pi divided by 6 would be pi thirds. If pi is 3.14, that's just a little bit greater than 1 radian. Right? Okay. Now, here are some common angles. Get to know them. These are going to be our favorite angles for quite a while in this course. Let's start with this. That's 2 pi radians. There's pi radians. There's pi halves radians. I'll jump up here to pi fourths radians. Then let's go back to pi radians and split this into thirds. So that's 1/3 pi, another third pi, another third pi. So that would be 1/3 of a pi. And then break that into halves. There, there, and there. And that's 1/6 pi, 2/6 pi, which is 1/3 pi, 3/6 pi, which is pi halves, 2/3 pi, 5/6 pi, and again pi. So there's splitting into 6. Now, later we'll assign degree angles to these, and these will be our favorite degrees. We're not talking degrees yet. We're only talking radians. But there they are. Those are the ones we're going to learn and deal with and have the greatest relations with. Now, one thing I wanted to point out to you, when they draw pi halves radians, we have a special name for that angle. Anyone know what we call that? A right angle. Okay? And here's what I've heard. I think this is probably true. The Greeks are the ones that named it that because they thought it was the perfect angle. Because that's the one where you have the greatest strength. If you build a wall that's leaning this way or that way, it's likely to fall. You build it this way, that's going to be the strongest wall. Hold up the greatest thing. So they called that the right angle. Why they didn't call it the left angle? I'm left-handed. I would have. No. Okay. They always thought that was right for right. Okay. So that's called the right angle. And that's the symbol we use for a right angle. If we know it's a right angle, you can put that little box there indicating that is a right angle. Pi halves measure. Okay. Now, in just a short time, we're going to talk about special things about right angles and straight angles, which is pi. Okay. Okay. Now, again, we know the 4 quadrants of a coordinate system. We've already talked about this briefly. We named that quadrant 1. Everything's positive there. Quadrant 2, 3, and 4. Now, I don't know if that's where the counterclockwise came from or if they named the quadrant after the counterclockwise. I don't know which. But when you're talking in terms of angles in radian measures, in the first quadrant, you're between 0 and pi halves. In the second quadrant, you're between pi halves and pi. In the third quadrant, you're between pi and 3 halves pi. And in the fourth quadrant, you're between 3 halves and 2 pi. And 2 pi and 0 are, what do we call those? Same terminal sides, so we call them coterminal angles. Okay. Now, since we're naming things, let's do these two. If you're in the first quadrant there, between 0 and pi halves, those are called acute angles. Acute angles. Okay? Acute angles. And if you're over there in the second quadrant, between pi and pi halves and pi, those are bigger ones. You call those obtuse angles. What about what do we call it if it's right at pi halves? Right angle. There you go. Okay. Trick question. We just talked about it. And the pi is called the straight angle, by the way. So, acute angles are any angle that's between 0 and pi halves. Obtuse angle is between pi halves and pi. Later we'll name another angle that to me is easy to confuse with obtuse, but we're not going to hit it yet. It's oblique. And we'll get to that later too, but don't worry about it now. Okay. 2 angles are coterminal. We've already had this. They're saying it again. Two angles are coterminal when they have the same initial side and the same terminal side. So the angles 0 and 2 pi are coterminal, and pi 6 and 13 pi 6. Ooh, why would that be coterminal? Can you just look at that and see? Yeah. How about this subtracting 1 pi 6 and 13 pi 6? What do you have left? Subtract 1 from 13. 12 pi 6. 6 will go to 12. 2 pi! Anytime you have coterminal angles, their difference is some multiple of 2 pi. Going around in a circle. Okay. You can find an angle that is coterminal to a given angle theta by either adding or subtracting 2 pi, which is 1 revolution, to that. Or as many as you want to, but they're all multiples of 2 pi. Okay? Now, a given angle theta has infinitely many coterminal angles. It has that angle, 1 circle around, 2 circles around, 3 circles around, 4 circles, or 1 around the other way, or the other way, an infinite number of coterminal angles. But what's always true about them, they always differ by some multiple of 2 pi. So we'll say pi 6, say, plus 2n pi. If n is 0, that's just pi 6. If n is 1, that would be 13/6 pi. If n is minus 1, that would be 11/6 pi, negative 11/6 pi. Okay? So it's just always some multiple of that. And later when we're talking about all the angles that would give you solve this equation, if you're talking about them all, if pi 6 will solve it, then every 2 pi multiple of pi 6 increases that would also solve that same thing. Where n is any integer, not any number, integer. 1, 2, 3, 4, negative 1, 2, 3, 4, or 0. All right, here's example 1a. Okay. All right, here we go. Page 262. Now, I don't remember if I said this to you before, but I'm going to say it now. Did I tell you why I thought I don't like the publisher of this book, it's Engaged, but I like this author. Okay? Did I tell you why? Okay. If you'll notice here, here's example 1. Now, not all the examples will say this, but example 1 says, look at what it says. See LarsonFreeCalculus.com for an interactive version of this type of an example. Most of the examples do not say that, but this one does say it. That's a website. Anybody can go to that website, whether you bought the book or not. LarsonFreeCalculus.com is just a website, just like any other website. And you can go and see, in this example, an interactive version of this. Now, after every example, they have what they call a checkpoint. Okay? And look at what it says after that. Audio, video solution in English and Spanish at LarsonFreeCalculus.com. So every one of these that we will do in class, you can go home or go to another classroom or go sometime and do a checkpoint that will be similar to it. And if you can't get it, pull up LarsonFreeCalculus.com and they'll walk you through it. Now, at the end of each section, there are exercises. Okay? And in the red strip at the top of the page where the exercise is, look at what it says. See CalcChat.com for tutorial help and workout solutions to the odd number exercises. Now, I always will assign odd number exercises. Why? Because they have answers in the back. And if you check your answer, if you got it, go on to the next one. If you don't have it, come back and see if you can figure out how you missed it. If you can't figure that out, go to CalcChat.com. It's a website. You don't have to pay anything for it. It's free. It's there for you. And you can see that. Okay? Now, in this edition of the book, previous edition didn't have that, every now and then you'll see some of the exercises are in red. And they're always on. Or so far that I've seen they're always on. And what those are for is there's another place, and that's calcu.com. They have even more detail of what to do with that. No other book I've ever used has that kind of support for it. Okay? So in my mind, who needs WebAssign? Okay, now do y'all like WebAssign? Okay, if you do, I'll set it up for you. But what's the point? You have all this there. Okay, so let's see if we can we? I just probably talked it out. Let's see if we can do this. For the positive angle 13 pi 6, subtract 2 pi from it to obtain a coterminal angle. Well, what is 13/6 pi? Well, I'm sorry, 2 pi. How many 6 is that? Second? No, 6 pi would be 1 pi. 2 pi would be 12/6 pi. Okay? I like to think in terms of food. So pies, okay? Let's do a pie instead of pie. If you have 6/6 of a pie, if you cut a pie into 6 pieces and you eat 6 pieces, how many pies have you eaten? A whole pie. So if you ate 2 pies and they were in 6, you had to eat 12 pieces. Okay. Ooh, that sounds good to me. Okay. So that would be 12/6 pi, right? We'll subtract 12/6 pi from 13/6 pi and you get 1/6 pi. They didn't show that, but if you do your denominator, in other words, to get the common denominator of 6, multiply the denominator, which is 1, by 6, you get 6, multiply the numerator, 2 pi by 6, you get 12 pi. 13 pi minus 12 pi. 13/6 pi minus 12/6 pi is 1/6 pi. Okay? Which is shown here. 13/6 pi is 1 6 2 6 3 6 4 6 5 6 6 6 7 6 8 6 9 6 7 10 6 11 6 12 6 13 6. Okay, that's all the way around here. Subtract 1 pi off. And where are you? I mean, subtract 1 time around off, and you go back to here. 1 time around from this point to that point, and you're at 1/6. Does that make sense? Good deal. Okay. Do we have time for B? For the negative angle, negative 2/3 pi, you could subtract, but easier to add 2 pi. And how many thirds are 2 pi? 5? Huh? 6. Yeah, 6/3 pi. Well, 6/3 is 2, right? So that's 6/3 pi. So let's add 6/3 pi to negative 2/3 pi. What do you get? 4/3 pi. And that's exactly what they get here. Look at that. They did it well. Okay. So basically what you did, you started off with a negative here. You got over to here. And you're going to add 2 pi to it. You go back counterclockwise 2 pi, which brings you right back here. That's 4/3 pi. Now, in the graphic here, remember 1/3 of the pi is about like this. There's 1/3, there's 3/3 to make 1 pi. So that's 1/3 pi, 2/3 pi. That's negative 2/3 pi. This is positive 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. Yeah. So you can do it graphically, you can do it analytically with fractions. It all works. Either add or subtract 2 pi or some multiple of 2 pi and get your other coterminal angles. Okay, and then the checkpoint here is determining 2 coterminal angles for these 2 angles as well. I'll let you do it, and we'll start next time with complementary angles. If they're cute, you're going to complement them, right? Never mind. Okay. Now, out of time, sorry about that. But remember, audiovisual solution at LarsonFreeCalculus.com for all those checkpoints. Homework exercises, I think you can do 7 and 9, odd number 7 and 9. You can do 11, it has 2 parts. You can do 13, it has 2 parts. You can do 15, it has 2 parts. And you can do either 17 or 19. 15 and 17 are also on calcview.com, but all the odds are on calcchat.com. Sorry. Don't do 17 and 19 yet. We haven't done that. Stop at 15. Stop at 15.
7, 9, 11, 15.
Yeah, either 7 or 9 or both. 11, 13, 15. Right. And 11, 13, and 15 have 2 parts. So they're pretty easy, pretty short. Good deal. Any questions? We'll pick up and go from there next time. All right, good deal.